Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about capacitors connected to a battery and talking about the equivalence capacitance when they are connected in series versus in parallel. Okay, so let's get started right away. I'm going to do examples 16 and 17 in this video. So let's do it. Two capacitors of capacitance 12 picofarads and 4 picofarads are connected in series to a source of potential difference of 16 volts. Calculate the charge on each capacitor. So if we do a quick drawing of this one, I'm actually going to use a smaller pen. We have two capacitors connected here in series, and since they are connected in series, the charge stored on each capacitor is going to be the same. Okay, so the 1, 1, 2, 2, this is all going to be the same. And I'm just going to call that total because essentially what I could do is I could combine these capacitors into one capacitor, one equivalent capacitor, in which the charge stored on this one is going to be the same as either of these capacitors if they are connected in series. The reason being, since the capacitors are connected in series, the current running through them must be the same, therefore charge stored must also be the same. So if we find the equivalence capacitance first, we can use the potential difference to figure out the current. So assuming the battery is connected like that. Okay, so let's go in calculating this. Equivalence capacitance in series, it's going to be like this. And I'm going to put CE for equivalence. And the reason why it is, this is actually, I'm just going to put in the 12 picofarads. So what I'm using, I'm using this guy over here. Okay, or C total equals 1 over C1 plus 1 over C2, etc. What does your data booklet use? Out of curiosity. So the reason why it is going to be smaller is because the potential drop across each of those capacitors is going to be less than that of the battery. So compared, I just saw overall, C parallel. Okay. Over the battery, so that the overall charge that each capacitor can or will be able to store is going to be less. So it seems like the overall capacitance in the entire circuit is less than what it was before. So that's 1 over 12 picofarads plus 1 over 4 picofarads. Okay, so if I calculate this out without taking the inverse, so you just got to be careful here because especially we have to take the inverse at the end. So if we take this is 4 times 3 times 3, this is going to be 4 over 12, and of course this simplifies to 1 over 3. And which means if we take the inverse of that, the equivalence capacitance or the total capacitance is just going to be 3 picofarads. We have the total equivalence capacitance. So then we can use that to find the total charge by using the voltage as 6 volts. So if we find the charge, this is going to be CV, which is the capacitance equation rearranged. This is 3 picofarads times 6 volts. This is going to be 18, and since this is times 10 to the power of negative 6 times 10 to the power of, negative 12, I mean, this is in coulombs, which is essentially 18 picocoulombs. There we go, okay? So, 17. Find the charge on the potential difference across each capacitor below when points A, B are connected to a battery of 12. So, imagine there is a battery here. This is 12 volts. And the capacitors all have a capacitance of 12 picofarads. Oh, that's easy. So if they all have the same picofarads, then the same capacitance, we can do our simplifications right now, because that's not going to be too hard. Okay, so we have, we're going to do a simplification here right away, because we'll need to figure out a few things. Since we know that the total voltage drop is 12 volts, we need to know, first of all, if we know the total charge that can be stored on X, we can use that to find the potential drop here, okay? And once we know the potential drop across the 12 picofarads, this X capacitor, then the remaining voltage drop will be the same for both Y and Z since they are connected in parallel. If we know the voltage drop across this, we can then use that to go back and figure out the charge stored, which the sum of the charge stored on these two capacitors should equal the total on X, on capacitor X. So less talking and more doing. A lot. So that's usually why I like to, that's my students all the time. They need to do less talking. Okay, so let's do a simplification here. So we got A, we got B. I know this is very small. I'm going to zoom in. So I'm going to simplify that capacitor, those two capacitors in parallel. So here I have a capacitor here, which I will not touch. That one's going to be 12 picofarads. This equivalent one is these two Y and Z combine. Y and Z combine, according to capacitors attached in parallel, we have to add the capacitance there. The equivalence capacitance of XY is just going to be 12 picofarads plus the other one, which is exactly the same, and both of them added together is going to be a total of 24 picofarads. So this guy is 24 picofarads. If I continue to simplify this with A and B attached, if I want to, say, add these two capacitors together to give me the equivalence capacitance here, I need to add these two in series. And we know if we add them in series, or I'll just call it E, this is going to be 1 over 12 picofarads plus 1 over 24 picofarads. So this is going to be 12, this is going to be 3 over 24 picofarads, or 1 over 8. So if we take 1 over C, CE, the equivalence of the total, this is going to be 8 picofarads, okay? So 8 picofarads is going to be my grand total for these capacitors then stored in series. So if I put them, now we need to find the charge stored. So we know that the overall voltage drop here is 12 volts, I think. 12 volts? Yes, 12 volts. So that's a total voltage drop, okay? Total voltage drop is going to be 12 volts. We know that the total equivalence capacitance is 8 picofarads. So we can use that to find the charge stored, which is just CV. CV is just going to be 12 times 8, 12 volts, times 8 picofarads. This is going to be 96 picovolts. Is that picovolts? No, sorry, pico coulombs, okay? So a total of 96 picocoulombs stored on the first one, which we can then use to calculate the voltage drop across the first capacitor. I believe that's capacitor X. So for capacitor X, we know that the charge is going to be the same as the total charge since it's attached in series. So we know this one. We also know that the capacitance is 12. We can then figure out the voltage drop. Oopsies, picofarads here. The voltage drop is going to be Q over C. So this is 96 picocoulombs over 12 picofarads. Pico. And that's going to be 8 volts across the first one. Okay? So if we know that the first voltage drop here is going to be 8 volts, the remaining has to be 12 minus 8 volts is going to give us 4 volts for the remaining drop. Okay, so now we know the volts of the remaining drop. Let's use that to calculate the charge stored on Y, which is going to be exactly the same as the charge stored on Z because they are the same capacitor connected in parallel. So we know that the volts is going to be 4. We just took the difference. We know that the capacitance is still 12 picofarads. The charge is not going to be the same because imagine in parallel, these charges are going to get divvied up between Y and Z depending on their relative capacitance, which is the same, so they're going to get the same charge. But alas, let's go ahead and calculate this out. Q, we know, is CV. And based off of that, we have 4 volts times 12 picofarads. This is going to be 48 picocoulombs, okay? So 48 picocoulombs is going to be the same, for Z as well, okay? So Y equals a Z, in which the volt potential difference is going to be 4 volts, and the charge stored is going to be 48. And the cool thing is that 48 doubled is 96 picocoulombs, which is the total charge that is stored on X. So it works out very nicely. Okay, so there you go. That's the question on capacitors hooked up in parallel versus in series. So, hopefully you learned something in this video. I wish you the best of luck with your problems, and Mama Physics signing out.